Why do I get an error in YouTube? I don't know. I can't watch myself. Yeah, let's not think about it. Copy everything, even what we don't need. Hey, little Jip. Right. Well, we do get something. Okay, how shall we call this thing? No, it's too long. Cubic. Cubic extension of a quartic. See if that is a word. Yeah, fourth degree thingy. Okay. Now let's include negative numbers, but run from -8 to 8. The x range, kind of the same thing, I guess. Just randomly 10 to 10, or then maybe better powers of 2. and I want to be able to drag points around. In fact, I want to be able to drag points around and then create an arbitrary fourth degree polynomial that goes through a fixed point. Let the fixed point be, yeah, I don't know, somewhere. Not 0, 0, right? You never know what special case you conjure with that. In other words, make it a variable, or well, a constant. I can define that here. So make a const expression, double. X1 is, let's say, 0.5, though more or less in the center. And put this one at 3/4, so let's say 4. I wish I had an AI that could tell me how to draw a point in this place, but we don't, so I'm going to need to have a look at the previously written programs that already have that code, because I just forgot how to do it, obviously. I have no idea. Let me just look at all of them. This is the one that I'm writing. This is, look for the word drag. It's probably there. In fact, let's just grab for drag. Register draggable. Okay, that's definitely what we want. GC register draggable, and then we see that we have a few options like clamp check. Let's see what clamp check is doing. Okay, yeah, so there's a draggable point with a circle, and we can rotate that. This allows me to make an arbitrary cubic. I need to be able to make an arbitrary quartic. But this gets pretty close, doesn't it? I want to make, so one point must be fixed, so we can't drag that. It's just only the derivative can be changed. And then maybe make this one indeed draggable, we can do stuff. And then, yeah, I need something else. So make it a fourth degree thing. Maybe we should just start with this. So how is this done? Yeah, so I need 2 points. What is S1 then? S1 is a random sample. It's the starting values. To pass a second derivative. I have no idea what it's doing. Just looking at it, looks like it will compile. Oh, really? Unknown sample. Undeclared identifier gradient descent. Where do I get my sample from? This one. That compiled. And nothing. Probably because the circles are drawn outside of the window, I guess. The Y values are way too big. 47 something. Okay, so this is the Y value then. No, let's make that Y1. And this one is then the X value, I suppose. Let's put the other point at another starting point. What is a good starting point? Minus 6.0. Height 0.0. Okay, I do see a point here at minus 60 and another one at whatever that is, 4. look good. And then this one is not draggable. This one's also not draggable. That's not draggable. It's absolutely, there's nothing draggable. And that the reason for that is that I'm missing a loop, I think, somewhere. So let's have a closer look at the clamp check. You can register draggables, but then we need a loop. That's a while true here. Okay, so just copy that. Plot a circle and a label and an arrow, and we get a direction. Plot the other one. Probably need all of these as well. Might as well print them, and then we can calculate a cubic. Okay. Just stop there. No, wait. That just the cubic is more complex. We have to include this to make the cubic. And then I can draw the cubic. Oh, might as well do that also. Yeah, this draws a minimum and maximum of the cubic. That's already so much. Let me just paste that in here. And then from the bottom we get something like this, I guess. Should do it. Who needs documentation? Just blindly copy stuff. Okay, no label style. Let's put that on the point style. Oops. Looks suspiciously much like this one, so I'm going to delete that one, I think. Polynomial is not known. Right, good. The points are still at the same place, but now we can drag them. And this also, and the cubic is generated. Yeah, this is just I just copied the code. Okay. I don't want to make this point draggable though. It just should be fixed. So let's change that. I guess that's point 2, or yeah. 0.1, P1. Make draggable P develop, make draggable P1. So we don't do this, and it should no longer be draggable. Bleep. Okay, so this is still draggable, but and that too. Really? Oh, this is P1. Okay. So the other one then. That one must be draggable, but P0 must not. Now I want to make it a fourth degree polynomial. And I have an idea, I think. I'm also going to need, let's see, so this now works. I'm also going to need a vertical line here somewhere that I can drag from P0 to the right. And then maybe where that line intersects the I just have a point on that line as well. This is another draggable point then with a vertical line through it. And then just demand that the fourth degree polynomial goes through that point as well. It should be fittable, right? So I need another point that can be dragged, but is limited to on the right of P0. So let's do create a point P. Oh, it's not on my keyboard. Two. And now we need a new sample apparently. Let's begin with putting it on the same spot as the other one, except a little bit further to the little, not exactly. Let's, I don't know, 1. And then down a lot actually. So -8. Oh yeah. And then way more steep, I guess. I don't know what yet. Let's just copy it once we get it. This is the starting point for now. The thing does not have a circle, but it must be draggable, so we repeat this. Okay, what's Q? Oh, Q, sorry, yeah. Q is just the point on the circle, but we don't have that. So we have just a new position. And then this code moves a Q. I don't want to do that. I want to add a limiter, which is more like this. So you get the new point, and this is a reference to the plot and a reference to the, this is a lambda, right? So is larger than, yeah, P1 actually, X. Oh, that's good. It's not allowed to be less than or equal, let's say. So if it is, well, if it's, what can you do? Yeah, just gonna add epsilon or something. So I want to change P2 to become a point that is equal to P1x plus some epsilon value, comma P1y. So if the x value of P2 is on the left, then we put it a tiny little bit on the right. Then need access to P1 though. To pass that as well. Of reference P1. Do we have P1? I don't think so. I just have plot P1. So really, this is just plot P1 is derived from KO in the point, which has the x and y members. So that works as well. So that plot P1 is then passed to the lambda as a reference to the same plot P1 that we have created here. So here's a new point which we cannot drag around. It's being forced to the same position. That's strange. Yeah, completely fixed. It's also not a not a function of this. Oh. What am I doing wrong then? I really don't get it. This should not even be true. So we should never execute this. So it should just pass back whatever plot P2 is, which should be the value that we drag it to. But I'll comment it out. See if I understand register draggable correctly. So we get a new position. Oh, it's called new position. Whoops. Okay. Yeah. What is this then? Let's see. Register draggable. Oh, this is just the thing that you want to register, but the new position is what it is being dragged to. Okay. So I need to use the new position, obviously. Cannot change the new position though. Okay, but if the new position is wrong, then put it here. But of course not use the y value of P1, use the y value of the new position. You can definitely drag it vertically and it's only clamped if this is true. Now it should be good. No, still nothing. What the heck is going on? What am I doing wrong here? This one returns p1 plus something. Circle radius times d1, where d1 is deduced from a new position. Okay, I should not return plot p2. I think I have to calculate something myself. Sorry, I have to make my own point. Result. Oh, I'm a bit not clear about this, I must say. The clamping then looks like that still, and the result starts with a new position. Can't change new positions, passed as a const reference, so you have to make a copy. And then we change that and return that. Maybe the previous code would have worked if I just copied the new position to plot P2 first. I think that's being done after it's being assigned probably after returning. Finally. Okay, so now draggable here, but if we try to go to that side, then it's not clamped. We can drag it anywhere we want. How the hell? I must use P. I didn't drag it far enough, I think. It must be P0. We're no longer using P2 for some reason now. Is that not weird? No, probably not. Huh? Yep, now it works. Okay, so if the mouse goes too far this way, it sticks, and otherwise we can drag it on this side. Now I want to have a vertical line through it, and I can probably find that by assuming I called that before vertical line. I didn't. Maybe something that looks like it. Vertical line through something. Yeah, okay. Plot vertical line through algorithm. That's not a test. This is a test. Here we have two vertical lines. Let's have a look at this example. Okay, so we can make a plot line. By giving it a random point with the correct x value and a direction, and then add that to the plot. Just copy this, I guess. I mean, that should be enough information to succeed here. And this must be drawn inside this loop because it changes its function of dragging. Let's do that here. Yeah, might as well immediately construct it. And we have an x coordinate. Let's see, so some x coordinate and then a random y coordinate and the x coordinate, and should be x coordinate of the last point as p2. So plot p2x. And then it's using line style. I'm not sure if I want that. Line style is has dashes. Okay, it's good. That's I want dashes. Or maybe I don't. Well, we'll see how it looks. Yeah. Okay, vertical line is there. Now to make this a 4-degree thingy that goes through this point as well, and then we can make a random 4-degree polynomial. So blah, blah. My polynomial can be made 1 degree higher. It's not called a Q, I don't know, let's call it f of x. Yeah. I don't like short names like that. Cannot grab it. What was it called? A quartic. For debug output. And then, yeah, how can we create those things? That's maybe not that easy actually. I just have to know the coefficients. Oops. Yeah. I have a link here where I derived this for a cubic. So that is going to be not easy whatsoever. Shit. Can ask an AI, but AIs don't know that kind of stuff usually. But hey, let's try it. log in. Yeah, but do you sign up, log in? Let's say just click login. Oh yeah, and then we get this. I really don't want to do this. Huh. Maybe just not talk about points at all. The derivatives or some derivative value. Let's before asking something completely impossible. Let's think about it a bit, because so a quartic has the highest degree is 4. So we have 5 coefficients, which means we need 5 equations. and I count 1, 2, 3, 4, 5. Okay, makes sense. Let's ask this. Uh-oh. Oh, there it is. It isn't very stressful to test if AI makes a mistake, because you just copy it, and then if it is correct, you will immediately see that in the simulation. Oh shit. Should probably just insert this matrix and solve that. Using a library. Let's see if we can get the actual formula from Wolfram. What? Interpreting as solve XCO to the power 4 equals 0. No, it's not what I said. This shit is so unusable. It's almost never possible to ask a question without it failing. I'm surprised that, I mean, I copied it the way it asks it, I would say. But that should have math input. Let's try that one. Still interpreted it completely wrong. What is this? It's kind of a weird something here. I think my copy didn't work. Yeah, I mean, why would that not work? It completely fucks up how it is even displaying it. Yeah. Go pro now. Yeah, I'll pay for this. Sure, no problem whatsoever. Let's do something else here. Okay. How can I solve this? Oops. How can I solve this using Octave? I think I already know how to do it because I kind of learned it from seeing examples of from the AI. So I have here this one, for example, and we're going to make solve I don't know, heuristic .m. So we need to begin with defining the symbols that we have. I think the only symbols we have here is, well, X, maybe just A, B, C, D, E. Something like that. And it can define a 4-degree polynomial. Probably. So we make a 4-degree polynomial, and then we make the derivative of that. We probably might need that as well. So we have dp. And then that shows you complete idiot. Complete idiot. Yeah, no. I just go back to my own thing, which is repeated here. So we have 5 equations being oh, we have all these as well. Yeah. Oh, x0, 1 and 2. So add those as well then. x0, y0, x1, y1, x2, y2, and d0 and d1, right? Bloop. Yep. So you can make an expression for the f of x of 0 by doing a substitution. So we're going to call that p x0 is, and then still how to do that. So we just a sub. So you just sub it with something. I will make an equation here directly, but yeah. Oops. N. So replace in P all occurrence of X with X0. And, well, we need to do that for those two as well. And then we have a dp at x0, I think, was it? The derivative at x0. Substitute in dp x with x0. And the dp at x1 is substitute in the derivative of p x with x1. And then we can make equations. For example, equation, well, let's start counting at 1 on the, for change. So this one is equals y1. Y1. Equation 2 is px1 equals y1. Equation 3, maybe it would have made more sense to just start there because I have so much in common. Yeah, it was 0, of course. But they go through those points, and then the derivative must also be equal. So we have equation 3, which is that the derivative at x0 equals d0. And then equation 4 is that the derivative at x1 equals d1. Let me display one of them just to get a feel for how that looks. History, grab octave. Yeah, I'll just use this one. And the file name was solve_colic. Yeah, so you see that this is the derivative of p with x1 filled in, and then that's set to d1. So we have a d1 and a d, but they are really different things, so it's no problem. So then the question is how to solve something. I had equations here as well. Yeah, equations, and then we do solve. You should be able to solve them in parallel, of course, but that went wrong. It's kind of shitty. So since I had only 2 equations here, I solved one. So I solved b, but in terms of a. And then I replaced fill in that result in the other equations. But now we have 5 equations, so that's going to be a lot of work. I would rather do it in parallel. Solve should be able to do that. So let's do run octave and then do help solve. Did not load that package yet, apparently. It has no clue. Okay. Seriously? Let me ask another AI. Thought that this one failed already. I defined 5 equations in Octave. Do I continue in Octave to solve this set of 5 equations? Q0 to AQ4. That I have my doubts, but we can start with it. Space solution. Holy slow. Okay, this starts to be ridiculous. It is using CPU. 1 core. I don't think this works. Let's try it. Let me think. I think that the yeah, I think you have to do it in C++ using a math library. Seriously. It's completely got my prompt back. Okay, now I have to remember, of course, that where I do that, I'm having somewhere I'm solving something with, I forgot how it was called. Seriously, a memory, man. If you get older. I think I should be able to see that in the CMake file. eigen, yeah. We solve it using eigen. So if I search for eigen in my code, there it is. Example matrix inverse. So here it happens. It does solve a matrix equation, but okay, let's go back to ChatGPT. Now let's see if that makes sense. So we have this matrix, and now we multiply that by the things that we want to know, A, B, C, D, E. A, B, C, D, E. So A, B, C, D, E. Yep, 3 times is y0 up, and then this is for the derivative. So that is 4A. Yeah, 4 times x0 to the power 3, and then this 1 and here 0. Just remove the A, B, C, and D from it, and you get it. Hence, this is a 0 because the E drops out, and this is these are 1s because D is just on its own. And that equals that. So that looks good. And then we just say, please write a C++ example how to solve this using eigen, and what was it, eigen 3? Or does that not matter? Eigen 3, yeah. Okay. Eigendens. And then yeah, every time I drag a point you have to recalculate it. Hopefully this is faster than Octave. So we're going to need this is x0, this is y0. Forget about that. I don't need a second derivative, do I? Not in this case. Well, wait, that is just the first derivative. We do need that. This is d0, right? And then we can do the same thing for 1. X, y, and d. And we can do the same thing here for x2, oops, y2. I really can't type. Y2 from point 2. Now forget about that. And then we're going to solve this thing. Let's see, the fitter uses cubic. This is not gonna work. Cubic. Substitute cubic with quartic. So we must solve the thing, and that then works as follows. Well, we have these calculated. So we create a 5 by 5 matrix, and then it should compile. All right. It actually compiles. It even links. I'm surprised. Apparently we're linking with eigen already. No, we're not. Let's add the linking as well immediately before we get linker errors. So eigen is linked with like that, and we're working on this one. Okay. Still links. Then we write that. Bleep. Okay, with this one time using POW, standard POW. I think this should compile, right? If you add the header, that is. Okay, all those headers, and I didn't include CMOD. Shocked. Oh. Oh, it's sorry. Never mind. It's not the type. How do you do this? Make POW equal standard POW. I have no clue. Not even going to do it. If someone knows, tell me in the chat, okay? I'm open for it, but there, just use std. Okay, that worked. Next, create a vector of constants, right hand size, okay. Yeah. I just copy everything. Bling, bling, ping, doing, gadang. And it compiled, so let's run it. Maybe a bit too lazy. Yeah, there we are. So here we have already the coefficients, and if I drag this thing, then and it is fast, as you can see. That's the speed that we need. Good. But now to convert these coefficients have to be placed into my quadratic. So instead of printing them, we're just going to assign stuff. I don't need to print this. Let's just say quadratic I equals that. Hopefully they match. Int I is 0, I is less than 5, plus I. And then we can plot it. Well, that doesn't look like it's a correct thing at all. It's not going through any point. So maybe I just messed up the order. Hopefully. So I'm going to guess that this is 4 minus I. Please make that work. I don't think any mistake was made by the AI, and I copied everything correct, of course. So yeah, this should work, and it works. Great, man. So yeah, it looks a bit wild, but we can of course. No, I cannot. Oh, okay. This looks a lot better. So now we have a nice 4-degree polynomial that goes through all 3 points and maintains the derivative and continues to go through this point here. Now, usually I would have something like the points pretty close together, at least these points pretty close together. You can end up with something like this indeed, and then this a bit deeper, so something like that. Now, what actually I had a problem with that. This was still positive, so on the wrong side of. I still want to have this one close, but. It's not what he wants. I want a minimum on this side. Oh yeah, okay, now we have a minimum on this side. Yeah, like that, that's what I want. So this derivative is still a little bit positive. And then let's say, yeah, and then if you do this, you make it closer, then the minimum of the fourth degree polynomial is like way over there. So even you can even put it, yeah, no, but you know you can't see anymore where it is. The scale is a bit too small for this. So I just have to put it here. I want to see it. So. Okay, now the beautiful thing starts, because now we just created a fourth degree polynomial and we can pick some distance here. I move that to this side. It changes in all kinds of ways. Yeah, you have to live with it, I guess. What I want is to get a feeling for a cubic that it goes through P0 with the same derivative, and hold on, and has if you integrate the vertical distance between the cubic and the quartic over the distance from this point till the dotted line squared, then the cubic must be minimal. Yep. So it's saying, oh my god. So yeah, well, you didn't get it. We want to draw a cubic. The cubic must go through this point and have this derivative, and then we have two more variables left that we can fit. And those two variables must be such that the quadratic error is minimized. So quadratic error relative to P0. But I already have the formula for that on a piece of paper, I'm afraid. So we can, actually I want to keep this and not have to drag every time to get to this point. Unfortunately, the only way to do that is to print the values. Well, this is maybe not that precise. You know, put it somewhere, but let's put this at -2, -3. Yeah, but also the derivatives changed. Damn it. I have to print all samples and then do this again and then copy the values. Oh, that's not going to work. I don't think the samples are updated. They're just constants. And I called them as one, and it's just for some reason we start here with never put two on the same line, dude. But these are the coordinates of P1, I think. These are the coordinates of P0, and these are the coordinates of P2. So let's bloody rename them. X1, X2, rather. Yeah, 0 is created from S1. So let's rename this to S0. So all the S's one less. So I can print the samples now if I just create them from x, y and the derivative. So we create a sample. We make the sample from plot P0x. Can I not? How can I make my samples? No, just 3 doubles. And now we need the derivative of the quartic. So where's my quartic? Quartic dot derivative at this x coordinate. It should give me the derivative. Let's see if that works. So my quartic was this polynomial. Symbolic, 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 symbolic. Cubic polynomial. Polynomial. I have a normal derivative, but not. It returns a polynomial, I mean, not one that interprets. Oh, it does. But no, this quadratic polynomial again. So we don't have that, so we have just a polynomial, which we again can evaluate like this. And then we do the same thing for S1 and for S2. Compile. Because if it compiles, it works, but unfortunately it doesn't. Too many arguments provided to too many arguments. Oh, it doesn't like the comma. Kind of surprising, I must say, but or did I forget closing something? Oh, that worked. So now we can run it again. And I'll drag this stuff back to where I wanted. So this was a little bit positive, and it was at I've got. And this was somewhere here. Nah, I want it like this. How about this? Like this, like this. Yeah, well, it will just have to do, except that on second thought. No, this will do. Which means that we have these values. Yep, plop, copy. So the half and the 4 are still there, of course, because well, we never moved that. I'm just going to put them directly in, I suppose. Derivative. What the? Oh, yeah, the sign of the derivatives are wrong, or it's completely wrong actually. The whole derivative is just bullshit. This is not a derivative that I used. I used something like this. And this one was like that. I think something went wrong with the derivative. To these values. Yep. So I'm putting a derivative in here, but the derivative is not being used. Why not? Because it's just being calculated. Calculated from what? No, I'm using the derivative here. This value is pretty small, and the arctangents of that value should therefore be, I guess, close to 0. It's phi 0. What's going on here? Clueless. To 1 radian. Oh, 1.0. I did. Huh? No. S1. Yeah, I thought I printed S0. Phi 0. Oh, I didn't rename these. Yeah, so where did I stop with renaming S? Probably, yeah, below this line. 0 to 2. No, 0 to 3 even. So this must be 1. Oops. 1, and this must be 0. Place 0. Place 0. Place 0. Place 1. And that's okay because that was new code. And then we go to the top. Good, 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 good. Yep, now it reproduces. Okay, so it was using this derivative here and this derivative there, I guess. Yeah. So now I want to plot the optimal cubic that goes through this point with this derivative and fits this quartic as good as possible over this interval. Which means that we have to define, after calculating the quartic, even after plotting it, yeah, maybe I should leave this for in case I want to copy it again. Let's make a cubic polynomial. Cubic. Which you can just pass A, B, C, and D. So, I don't know. Let's do something because I need a beginning. And then plot that as well. Suppose that code is enough. Plot the cubic. Cubic. Let's call this 1, 3. Nobody knows why to call it 3, but probably because it's 1 more than 2. And it's using W, but okay, W is X. And I want to have a little different color here. So we're going to adjust the style with dot line color is from the namespace color. I don't know, red. Maybe red's a bit too red. What is a good color? Maybe not red. Let me think. Just something different from, but not too light. Red will work, I guess. Yeah, just red is good enough. It doesn't know what cubic polynomial is, obviously. Include cubic. Okay, so that's our random cubic in the color red. And now I want to get my optimal one. And the formula for that is, for my paper, it looks like the derivative, actually. Yeah, I need that one. Okay, the constant, cubic polynomial. The constant is the first one, and then we get the higher degrees. So the first one is, well, can anyone has a guess? It's not that difficult. It goes through the same point as the quartic. And I'm using a Taylor expansion in the point relative to the point at x1, I hope. No, it's x0, isn't it? Yeah. So P0 is x0, so we have a Taylor expansion relative to this point. Which means that the first coefficient is the y value of that point, which is y0. Y0 is P0, and the y value of P0, and P0 was, well, we just saw that. That must be the correct point. Yes, because since this is the Taylor series relative to that point, it means that if the x coordinate equals x0, then the rest of the Taylor series is 0. And then, of course, we want to get y0 out of it because it should go through the same point. And the next one is the value of the derivative in x1. So that is x0, that is d0. That was supposed to be the derivative. And the next one is well, it looks like half the second derivative of the quartic in x1. So let's start with that. Half times the second derivative of the quartic. We could only get the derivative of that as a polynomial, correct? So I just have to do maybe should do that in advance. So let's say we have actually I think I can create a cubic. Let's call that dp and create that from the derivative that is returned from the quadratic, from the quartic, because this returns a normal polynomial, and then my cubic polynomial can be constructed from a normal polynomial, provided that it is degree 3 or less. And we also need the second derivative, so let's call it that. But now I can just take the derivative of this thing, the derivative, and in fact the cubic polynomial allows you to just evaluate the derivative. I'm going to yeah. And the second derivative even, so it's way better than polynomial. So we don't really need this one, but make a cubic polynomial that is the derivative of dp. Then this one is going to be not the first derivative, but the second derivative of p in the point x0 times a half. Did we do that correctly? I think so, yes. Second derivative, this is the second derivative of p then in x0. And the last one is going to be close to, but not exactly, but I'll fix it in a bit, the third derivative divided by 6. Okay, just do. I'll just divide it by 6. That is the dp, and then evaluate it at the second derivative at x0 divided by 6. This should work. Whoa, I had not expected it not to go through P0. Why would that be? It's going to x at x0. Oh yeah, of course. We have to shift it still. See, that's good that I didn't choose 0, 0 here. So this is the Taylor series, which means that it is going to be 0 if you fill in 0. Well, the last shift is missing. So that the y coordinate is correct, but the x coordinate still needs to be adjusted. Which means that we have to calculate that here differently. So we must do w minus x0, right? Then you pass 0 at you pass 0 if w equals x0. which means you have to capture it, but we capture everything by reference. Why not x0? Nah. Let's grab x0 by value. That is not how you do it. Okay, I don't know. How do you do that? This is the default. It's by reference, and I thought it was an equal sign, but apparently not. Maybe just x0. Probably just x0. Yeah, of course it's just x0. Again, a memory issue, man. Got that. So now it goes through the right point. But yeah, you immediately see that this is not the optimal solution. It's pretty close fit, but it has a quadratic error that we definitely could make smaller by making this whole thing a little bit wider, for example. Yeah, and then it just follows it as exact as possible. And then here, obviously, it's going to divert tremendously because this thing is going down, 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 down. But we're only interested in minimizing the error between this point and the vertical line. Yes? And doing that means that I have to adjust these things a little bit. This becomes that thing minus, oh boy, yeah, 15 divided by 28, which is a constant, I guess, times, I'm gonna write a for a moment, times s squared. I'll just write s times s. And this one is going to be plus 3 divided by 2 is 1.5 times a times s. Where a is the coefficient of the highest power in the quartic, which is probably just can get that directly from the quartic. So actually it is also equal to the fourth derivative in x 0, but I'm just gonna grab it directly, I think, from the quartic. So double A is the quartic at 4. That's the coefficient of the x to the power 4. And s is the distance between B0 and the vertical line. Which is given by, that was P2, right? So we have plot P2 x minus plot P0 x. GFDB, because what I'm doing has nothing to do anymore with gradient descent. It finds the minimum in a different way. Well, as you can see, the formula is correct in the sense that this is an exact fit on top of the chordic between this point and that point. So the error is definitely minimized. And then afterwards you start deviating, but you don't care about that. It's just about minimizing the error in over this area. So I think it's pretty cool that we were able to find a cubic that it has the perfect minimum error over that area. And I can drag it. No. And I don't know if you can see this on YouTube, so I'll make it a bit more sophisticated. But for example, in this case, yeah, it can't fit it as precise anymore, but so it goes a little bit below here and then above here and then below here again until this point. And this is really the quadratic vertical distance minimized. Use this cubic. But yeah, we don't want to do that. We don't want to go that far. It's only starts to become visible after you drag this over the minimum. At some point it must, I don't know, divert a lot. This is interesting that the cubic, that the quartic, I mean, has its minimum before the minimum of the cubic. The case that I ran into was the opposite. This minimum was just way to that side. So let's see if we can just adjusting it as well. This minimum is always on the right in this case. Interesting. Interesting. Often you have something more like this. No, this is not at all what I want. Maybe, yeah, something like this maybe. So again, it's but they're more or less at the same place, but it's always a little bit further apparently. And here they are almost at the same place. If it is on the left side of this point, the fit is of course very good, and therefore the minima is also on the same place, at the same place. It kind of has to be. No, it jumps away. Let's see. Cool. This is the insight that I wanted to get from this. Yeah, okay, so that's how it works. I'll explain what I am seeing. So we have at some point we have enough samples to fit this 4th degree polynomial, the quartic, and even without, I mean, we already have a scale. This distance is going to be the scale, and the scale is more or less the distance between these 2 points. So going to be, let's put it that way. So let's say this point was here, and this point is, well, let's put the point here. The distance is more or less 1, and then this over here, so the distance is also more or less 1. If we did fit a 4 degree polynomial through P1 and P0, then this distance is going to be more or less the scale that we have. And then we go the same distance again to that side. I wish you could switch vertical size. I can, of course, but then I have to add a slider here. But okay, at the moment we have this quartic and the scale, we can already find this cubic. So it's kind of an extra information, as it were. And it turns out, to my surprise, that that cubic has its minimum more or less at the same place as the quartic. And if it doesn't, then at the very least it's on the right. Well, that means that if we jump to the minimum of the quartic and then not get a point here, but get a point there, so the function, the actual function that you just sampled, has nothing to do with this quartic. So the quartic is good through P0 and P1, but it's like totally wrong for this minimum. This minimum should be way further than the scale, otherwise that should not be possible. And if I do that, then it's not, well, I just have to make the scale very small, I guess. So I'll put P1 like super close here. So now the distance is, that was a half, but looks more like a quarter of this distance. Now there must be a half. Okay, so now the distance is a half. And then the scale is, let's say, always also a half, so that ends up here. And then this is more or less going to be 0, might as well put it at 0. And then I need to change this so we get a sensible, can't get it the other way around, only 2 maxima now. Yeah, but I have it high, so let's put it then. That is not realistic. Sorry. What the heck? I have to put it even closer, I guess. Very sensitive. Very sensitive. It's just like 1 pixel and it jumps all over the screen. Well, maybe this would be an example then. So now at least the distance between P1 and P0 is more or less equal to the distance of P0 and the vertical line. And the minimum the minimum of the quartic is, I don't know, somewhere here, right? So several scales further. Very, very, very much down. So it's not totally unlikely that then the actual sample that you get at this point is not down there, but up here. And just gives us a cubic which goes through, say, P0 and this point, and then that cubic has nothing to do with the cubic that would fit this quartic. My objective is to recognize when the data point that we get is obviously wrong. And it's obviously wrong if the cubic that we get has nothing to do with the optimal cubic that you would like to get, which apparently is the case if the minimum of this new found cubic has nothing to do with that minimum, and it has definitely nothing to do with it if that minimum is on the left side, because it turns out that it was always on the right side, which then in turn means that, very simply, if we find a cubic fit with the new data point that has a minimum between P0 and the new sample, then I can just reject it. You must find a point where there's no minimum. Unless, of course, no. Well, yeah, unless it's almost at the same spot. So, for example, get that thing into sight again. So if we jump to this point and the cubic that we get has a minimum on the left, then we can safely reject it. That is just not interesting to jump to that point then. So then I will do backtracking and just half the distance. Or maybe just simply jump to the minimum of the cubic that does fit. This seems like always a good point to jump to. Maybe half that distance, I don't know. Or just the scale distance. But yeah, at the very least reject that cubic. So what I wanted to do is to move this thing so far, yeah, that the minimum is maybe on the other side. So in this case it has to be super close together, but I suppose it's now possible that this minimum is, because it's almost equal, it could be a little bit smaller, right? But a little bit on the left here. And then I don't want to reject it. That would be stupid. This is an absolutely perfect point to jump to. But yeah, if that only holds for minima that occur within the scale distance, then I would say if we find a minimum, so we jump to that, if then we find a minimum on the left of the jump point, but still further away than the scale distance, then we reject it. Something like that. I need to add an automatic vertical scaling, I think. It's not clear what is happening down there. Probably the same as we see when I do get to fit it on the screen though. So the minima are just more or less at the same place now. Yeah, beautiful. Okay, 8 o'clock here, 8 p.m. I'm going to make my dinner. I kind of finish this program. So definitely the end of the stream, and I'll be back tomorrow, I think.